All right, in the previous sections we learned about some ideas involving atomic structure. We looked at how to write electron configurations for atoms, but now we're going to backtrack a little bit and kind of delve a little bit more into some of the work that ultimately led into the development of Schrödinger's equation and the quantum mechanical model of the atom. Specifically, we're going to talk about light. Now, back in the late 1600s, Sir Isaac Newton believed that light consisted of these particles, but by the year 1900, most scientists had accepted the idea that light was a wave phenomenon. And according to the wave model, light consists of electromagnetic waves. Electromagnetic radiation includes radio waves, microwaves, infrared waves, visible light, ultraviolet waves, X-rays, gamma rays. There's an entire spectrum of all these different lights that range from low to high frequency or short to long wavelength. But before we go into the electromagnetic spectrum, we do need to make sure that we have a general understanding of waves. So a wave is basically something that oscillates about an origin. So in this case, for example, let's take a typical wave. When you wave at someone, your hand sort of motions back and forth, and usually about a specific origin. So you can say like that's sort of the origin, and you go like that, and you wave back, and so on and so on and so on, and you have this wave motion. So a more technical definition is the oscillation about an origin. That sort of defines a wave. So let's make sure we know the different components that make up a wave. So here, typical wave, our origin is this horizontal line. A wavelength is the distance between two consecutive identical parts or points on a wave. So for example, what I did was I picked the crest, right, or the local maximum of two consecutive peaks right here, and they're identical peaks, or they're identical points on the wave, and they're consecutive, so the distance between these two is a wavelength. But you also could have picked, say, this point right here. Well, the next identical point, notice how we're going downward on the curve, it can't be this point because we're going upward. It's not until this point that we're going downward again. So this is the next consecutive identical point. This distance to this distance would also represent the wavelength. If we pick the two bottom peaks over here, this distance and this distance would be the wavelength. And notice how in all of these cases the wavelength is exactly the same. So it doesn't matter what point you pick, just as long as you pick two consecutive identical points on a wave. Now, wavelength is represented by the Greek letter lambda. So it looks like that. Another term that's used to describe waves is the height of a wave from its origin to the crest. This is called amplitude, and that's really as far as we're going to go in terms of amplitude. We really just care more specifically about two components of a wave, and that's wavelength and frequency. So frequency is the number of wave cycles to pass a given point per unit of time. So let's just say this is our point that we're focusing on, and we have a wave, and a wave is constantly moving. So I know it's kind of hard to tell here, but just imagine that it's constantly moving. So if we were to take out a stopwatch and allow 1 second to pass by. Sorry, that's my baby asking for water. Okay, all right, so let's say that, sorry, I forgot where we were. Let's say that we have a clock, and we're going to let 1 second pass by. So the number of wave cycles, right, so that's wavelengths. The number of wavelengths that pass by a given moment in 1 second is called your frequency. Frequency is represented by the Greek letter nu, and the most common units are 1/second or reciprocal seconds, or the SI unit for frequency is hertz, whereas the common units for wavelength are some kind of measurement for distance, so it could be meters, nanometers, da-da-da. Now waves can vary in terms of frequency or wavelength. So in some cases you can have waves with long wavelengths, and if they have long wavelengths, then less will be able to pass a given moment or a given point in a certain amount of time. So the general idea is that the longer the wavelength, the lower the frequency. But you can also have wavelengths with waves with short wavelengths. So, for example, if we take a look at the green wave, the wavelength is significantly shorter. But since the wavelength is significantly shorter, more can pass a given position in the same amount of time. So a shorter wavelength equates to a higher frequency. And this is actually how we define all kinds of waves on the electromagnetic spectrum. The longer the waves, the higher the frequency. The shorter the waves, the greater the frequency. I don't know if I got that right. Let me repeat that for clarity. The longer the waves, the shorter the frequency. The shorter the waves, the larger the frequency. All right, that sounds right. All right, now there's a mathematical relationship between frequency and wavelength, and it's this relationship right here. C is equal to lambda times nu, right? So in this case, the speed of light is 3.0 times 10 to the 8 meters per second. That's about 8 times around the Earth in 1 second, so it's pretty fast. This value is equal to the product of the wavelength and frequency of any wave. So this relationship is real nice because it means if you know the wavelength, because you know that the product with frequency is equal to the speed of light, you can solve for frequency. Or if I give you the frequency, you can solve for the wavelength simply by rearranging. If you wanted to solve for wavelength, wavelength would be equal to the speed of light divided by frequency. If you wanted to solve for frequency, frequency would be equal to the speed of light divided by the wavelength. You just have to make sure that your unit for wavelength is meters. If it's something else like centimeters or nanometers, you do have to do a conversion first to meters. All right, now most of the light that you can typically see is usually a combination of several different wavelengths that give off that overall color. Sunlight consists of light that is just a continuous range of wavelengths and frequencies. The wavelength and frequency of each color of light are characteristic of that color. So when the sunlight passes through a prism, the different wavelengths then separate into a spectrum of colors. So here we have a prism, and as the light is hitting the prism and hitting this material at different angles, all these different lights sort of bend off at different angles, and you're given different colors for each of the different wavelengths that make up that light, and this right here is your spectrum. And a very common example of this phenomenon is a rainbow, right? So each tiny droplet of water that's up in the atmosphere acts as a prism to produce a spectrum. And each color blends into the next in the order of red, orange, yellow, green, blue, indigo, violet. Common little tool to remember those colors in order is Roy G. Biv. Or you could just memorize the colors. So it's always going to be in that order. And it turns out that red light has the longest wavelength and the lowest frequency, and violet light has the shortest wavelength and the highest frequency in the color spectrum. So the wavelength range for visible light is from about 700 nanometers to about 380 nanometers. 700 nanometers representing the longest wavelength, that's your red light. Your violet light has the shorter wavelengths, 380 nanometers. Now, this makes up but a tiny, tiny portion of the entire electromagnetic spectrum. This is the only part that is visible. I don't know why I'm writing that down. It's literally typed right there. Everything else is invisible, and by everything else I mean all of this is not visible to your eyes, and all of that is not visible to your eyes. So on this side, the UV light, X-rays, gamma rays, cosmic rays, we're looking at things that are less than 380 nanometers, single-digit nanometers, all the picometers, and you just keep going. These things your eyes cannot pick up. Also, waves that have wavelengths greater than 700 nanometers, your eyes cannot pick up, and anything greater than that. So wavelengths that are as long as micrometers, or as long as millimeters, or as long as meters or kilometers, those you can't see with your eyes. And so just to kind of get a visual, Radio waves are much longer, so you're looking at long waves. As we get closer, you'll notice that the wavelengths start decreasing in size. And then once we get to ultraviolet light, and we're looking at wavelengths that are much shorter, and they just keep getting shorter and shorter and shorter. Now that's the sun, right, which is a composite of multiple different lights. And the spectrum that the sun gives you is a continuous spectrum. But you can also have what's called an emission spectrum. Let's say instead of sun as the light source, we use hydrogen gas inside of a sealed tube, and you ran a current through it. We would see this sort of pinkish color. That's what we would interpret to be the color of hydrogen when electric current is passed through it. But if we concentrated the light by letting it only pass through a tiny slit, so we've concentrated it, and we have it pass through a prism, it turns out that it's not a single pink wavelength of light, it's actually a combination of 1, 2, 3, 4 wavelengths that give us that pink light total. And these are the 4 wavelengths that make up hydrogen gas. This is pink color when current passes through it. And here we have the wavelengths: violet, blue, green, and red. And again, notice, right, the red wavelength is going to be much longer than the violet wavelength. So this is going to have a higher wavelength, but it's going to have a lower frequency. And the violet light is going to have a smaller wavelength, but it's going to have a greater frequency. So this is what you would actually see in some kind of lab setting. So again, what you'll start to learn is that most of the light that you think you see, that you interpret, is actually a combination of different lights of different wavelengths that give you an overall color. So hydrogen isn't really pink, it's a combination of 4 different wavelengths. And the sunlight really isn't white light, it's actually a combination of all the colors of the rainbow. So it turns out that every element emits light when it's excited by the passage of an electric current or discharge through its gas or vapor state. Basically what happens is the atoms first absorb energy, and then they lose the energy. And when they lose the energy, they lose it in the form of light. And passing the light emitted by an element through a prism gives what's called the atomic emission spectrum of that element. And the emission spectrum of each element is unique to that element. It's basically like a fingerprint for each element. So this makes emission spectra extremely useful for the identification of unknown or inaccessible substances. So for example, much of the knowledge that we know of the composition of the universe comes from studying the atomic spectra of the stars, which are just hot glowing bodies of gases. So we look at their light, right? We take a telescope, we gather light from a star of interest. That light is then transmitted into an emission spectrograph to record the atomic emission spectra, and that's how we know what it's composed of. And here they're kind of turned sideways, but this is just basically a sort of quick visual from hydrogen to Einsteinium. Each one has their own fingerprint of atomic spectra. Now, if each of these were in a gas phase or vapor phase, when electric current is passed through it, you wouldn't see every one of those individual lights yet. You would see a combination of all those lights. And then once you run those lights through a prism, then you would see all those independent lights that make it up. Now, you might have gone to places and seen signs like this and say, oh, neon signs. And there's one correction that kind of has to be made there. Neon has its own characteristic color. So if you have a neon sign and it's that orange light, then yeah, that's most likely an actual neon sign. When you go back here, it turns out that many more signs that look like neon signs are actually just LED lights that give you all these different colors. For an actual discharged light, you have to have some kind of glass tubing with a gas inside of it and current able to pass through it. And LEDs work a little bit different, but people use LEDs these days because they're a lot cheaper and a lot more easy to maintain, and they have a lot more options in terms of colors. For your noble gases, when they're energized, their characteristic colors: helium gives you a pink light, argon gives you a lavender, Krypton gives you this whitish light, xenon gives you this bluish light, and neon is your traditional orange-red color. Alright, and then we're going to go ahead and call it here. Anyone who skipped to the very end to try and see if there were extra points given out, it doesn't work like that. You actually have to go back from the beginning and play through all of the video and then get to the end to hear about the bonus points. Alright, that's it.